um, redoing the proof that we did last time. We didn't quite complete it. And also I made a bit of a mess because I made too many corrections and probably it was not clear. Uh, so I want to revisit that theorem. But towards the end of the lecture, somebody asked a doubt, and so I gave the explanation. I feel that I should elaborate on that a little more so that you all follow why this problem, law of large number, the way I stated it, that probability that S takes values between two numbers goes to 1 is the same thing as probability of Sn by n. The same thing as uh, doing this coin toss experiment and observing what is the probability that Hn takes, I mean, the number of heads turns up uh, on an average in probability uh, as n goes to infinity is exactly equal to p, or is okay. So how are the two related? That's what I want to explain a little more. Okay, so I will start with that because this is very important and one should not leave it to just chance that you understand. So let me recall. So you have, I'll just write a little bit in not in elaborate way, but so these are independent. So these are family of independent sets. So family of independent sets, independent sets or events rather, events, and the probability of any one of them occurring. Okay, this is equal to P for all K. And what was the statement? So Sn is the indicator function, K going from 1 to n, indicator function of AK, right? And so we wanted to compute. So what is Sn omega? This is what I want to say. So Sn omega, what is it? This is cardinality is equal to, I write cardinality like this, cardinality of the set uh, of all K such that you see that is what it will amount to if omega is in AK, and here this K 1 less than or equal to K less than or equal to N. Okay, sorry, I write that clearly. K, this is okay. 1 less than or equal to K less than or equal to N. All right. So that is Sn of omega. And we are interested to compute. So what is the meaning of the statement that you want to compute? Okay. Let me write here. So this is a random variable. Okay, omega is in capital omega, and you want to know what is this set. So you want to know actually probability of this. Okay, for a fixed k. Now this is equal to probability that. So I am going to change this of the set. So this cardinality should be equal to k. Here k is a variable, here k is a fixed number. So I hope it doesn't cause confusion. And I'm going to change the label here. So, so this is set of all omega in capital omega such that omega belongs to exactly k members of A1 AN. Why only A1 A2 AN? Because Sn is the sum of the indicator functions. Okay, so you think about that. If omega belongs to A1, then it will contribute 1 to it. And now next you look at A2, if omega belongs to A2, it will contribute 1. Each time it belongs to a j, and j is between 1 and n, it will contribute 1. So if this adds up to k, that means omega belongs to exactly k members of this collection. And you are computing the probability of this. But you can write this because this is same thing as saying, yeah, so, well, we don't know which k it is, so I rewrite it like this. So 1 less than or equal to I1 less than Ik less than n, less than or equal to n, and then probability of AI1 intersection with blah 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 intersection with Ik, and it should not belong to the other one. This A. So let me write here AJ1 intersection AJ n minus k. All right. Complement. Okay. Where I1, I2, Ik, J1, J2, Jk, Jn minus k, that is exactly equal to the set. This is equal to, I just write it like box of n. Okay. So this means set of numbers, integers from 1 to n. Yeah. So it should belong to exactly k of them means this. But this is easy to calculate. This is equal to okay. So now you see this means that summation. Now these are all independent events. Pairwise, I mean that as a family it is independent, and now you prove that this is actually equal to probability of each one of these AI1 times blah 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 probability of AIK times probability of their complement, say J1 probability of A JK Jn minus k complement. And here, so I'll just write it briefly. 1 less than or equal to I1 less than Ik less than or equal to n. And this is exactly, well, so it doesn't matter what these values of these are. K of them, for k of them, you are computing the probability. For the complement of the remaining n minus k, you are computing the probability. And this means each one of them will contribute p power k, and this is q power n minus k. And now, so this is always the case, irrespective of these values, I1 less than, etc., less than Ik. And then how many ways are there of choosing a k element subset, and which you can always line up in increasing order out of this box n, exactly, and choose k. Sorry, I should have, yeah. So exactly k, yeah, that's right. Yeah, so there is no summation here. Now summation goes the moment I write here and choose k. Each one of them contribute the same thing, but there are that many. This is exactly probability of Hn equals k. All right. So now you can, after this, so I'm just now go back. So I don't need to, I suppose, expand on what is this Hn. Hn is the number of heads. Sorry, not number. Yeah, number of heads in n tosses, where probability of H is equal to P. Okay, so that's all right. So now recall the theorem very briefly. So given, so let epsilon positive be given. Okay, then you compute the average number of times. So let me write here a limit n going to infinity, probability of the set p minus epsilon less than Sn by n less than p plus epsilon. This is equal to 1. I already wrote limit, so I can write this is equal to 1. Is this clear? So that is same thing as saying, that is, I may write as well limit n going to infinity, yeah, probability p minus epsilon less than Sn, I write Hn by n less than p plus epsilon is equal to 1. So the nice thing about this thing is that, so the correct way to say that is that Sn and Hn have the same distribution function. That's what this means. And therefore they have, and therefore to compute probability that it lies between two ranges, whether you use this or this is the same. So, and you want to show this is equal to 1 and this is equal to 1. So these are equivalent statements. So, yeah. So let us go start off with the proof. So we computed this. So let me rewrite this. So we will be concerned with this one. So consider, yeah. So let me write here. So we need to show that. So we will show that. We will show probability of. So you may as well forget about Sn, but if you want to keep thinking in terms of Sn, that's also okay. So Sn by n bigger than or equal to p plus epsilon goes to 0 as n goes to infinity, and probability of Sn by n less than or equal to p minus epsilon goes to 0 as n goes to infinity. Okay, so it's like you just plot it and then, yeah. So in other words, I don't think I need to explain that because I already explained the meaning, why you should expect this P and so on and so forth last time. So, okay. So we will only do this, but the proof for this is exactly analogous. So we omit this second part. We just only do this, consider this part. Okay. And now, yeah. So let yeah. So m, because Sn is integer valued, so I want to take this n to the other side. So, and then I want to look at probability that Sn is bigger than or equal to n times this, but I may as well look at the ceiling function. So n times p plus epsilon. Okay. Yeah. Then probability of this required thing. So I'm going to write it now. Probability of Sn bigger than or equal to p plus epsilon is equal to summation. So m onwards. So okay, k equals m onwards. Let's write k here. K is the thing that is varying from m to n, and here, yeah, n choose k, p power k, q power n minus k. All right. Now we use that exponential function for lambda. So in other words, what we are going to do is replace each p power k by p power p times e power something lambda epsilon something, and likewise, so they will be weighted appropriately, which will allow us to uh, make use of some inequalities. Okay. So, and also estimate this. So we want to estimate this basically. So that's what we are going to do. So for lambda positive, we have, what is that inequality? Let me write that. Yeah, so e power lambda k is bigger than or equal to, is bigger than or equal to e power lambda n times p plus epsilon. Okay, if k is bigger than or equal to m, why so? Because so here e power, so this is like e power x is bigger than or equal to e power y for lambda positive if x is bigger than or equal to y. So that's the thing that we are using here. So replace that for uh, so this is equivalent saying that I can just multiply. So e power lambda k minus lambda times n p plus epsilon is bigger than or equal to 1. So I'm going to multiply each one of these ones by this factor, and then I'll have here this one is so I'm replacing by then. So therefore, so p of Sn bigger than or equal to p plus epsilon is less than or equal to summation. So k equals m to n. So here this is going to be split in this following manner. Uh, so okay, e power minus lambda n epsilon you keep outside. Can't do anything with that. Minus lambda n epsilon times. So there is also this n choose k, n choose k. This is going to be constant throughout, so it will be pulled out. So e power, so this lambda k, yeah, this k, we must write it as, so I, is a trick. K is k times 1, so k is equal to kp plus k times q. And when you write that, blue color, okay. So this kp will be paired with minus lambda np, so that np comes here. So that will become lambda minus lambda times n minus kp. So that will be clubbed with q, because q is the one which appears with with that exponent. And then what are we left with? This kq will be there. So I write p e power lambda q whole power k times q e power minus lambda p whole power n minus k. So this is what we get. Notice that minus lambda np is accounted for, and then plus kp is accounted for because I put a minus k here. And after this stage, you forget about this m, and then you rewrite this if at all you are adding some positive quantity. So m k equals 0 to n, and then you have, of course, e power minus lambda n epsilon. That's a constant. And then n choose k, e, this e is not there. Sorry about that. Okay. So what do we get? This is the same quantity I'm just writing. So p e power lambda q whole power k times q e power minus lambda p whole power n minus k. And now that fits into binomial theorem, which is equal to e power minus lambda n epsilon, which is going to be there throughout. And now you get p e power lambda q plus q e power minus lambda p whole power n. And yeah, so the next step is we want to replace this by something, okay, which is of course bigger than or equal to this quantity, but which will help us to make some simplification and so on. And the thing to do is you consider this inequality for any x. I don't know if you people did this. For any x in real numbers, what is the inequality? E power x is less than or equal to x plus e power x square. I actually tried to prove this, and I thought maybe calculus may be involved at some point or the other. And in fact, actually it turned out to be much, much simpler than what I had thought. That was okay. So let us prove this. Okay. So this is, we will get back to this, but let's just simply prove this because it's a very nice proof. Yeah, so it is good to know when these are agreeing. Okay. So you see, e power x and e power x square, they both agree when x equals 0 and 1. And one of the curve goes like this. Sorry, my figure is slightly skewed. Okay. The other one is a rather a little more steep. That is e power x square because it has to be symmetrical. And it goes down like this and like this. Sorry, I don't want to extend it here because it will. This is a very bad picture, I agree. X axis, y axis. Okay, so let me write this one is e power x, and this one is e power x square. Okay, and they both agree at 0 and at 1. Okay, yeah. So from the picture, it is clear that, yeah, I mean, e power x is actually this is all the information you need. Maybe you want to prove that it is like this and so on. If you like, you use calculus to show this. But this is evident that this is e power x is less than or equal to e power x square if x is less than 0 or x is bigger than 1, because they both agree, and this one is going like this and this one is much slower. So for this part, either it is pictorially obvious or you use calculus to prove this. On the other hand, if yeah, so x This is 1, no? Okay. This is 0, so this crosses it at 1, and this is E. So this is at E. Okay. 1 comma E. I should not write that over there. Okay. So, all right. So you need only prove this, that e power x is if okay. So yeah. So you need only check this if so we need to check. So we need to show that if x is between 0 and 1, then x less than 1, then e power x is less than or equal to x plus e power x square. And here you can make some cancellation, simplification, and so on, and then you just compare some term by term. Okay, after some small, so you will get some power series. You will get some power series here. Here there will only be odd terms. Here there will only be even terms. But look at the coefficients and so on, and compare term by term. After you cancel this x, and also there will be a 1 coming here when you write it in the power series. So there will also be a 1 here, and that will also get cancelled. The remaining term you compare, and then you see that this actually holds if this is the case. Comparing term by term. So that part I'll leave it to you. So exercise.
I think you've made some mistakes, sir.
What?
So e to the x and x plus e to the x squared do not agree on x is equal to 1.
When x equals 1, I get e. When x equals 1, x square is also 1.
So, but we also have the x here, so
No,
we
no,
get
I
e
didn't.
plus 1.
That's what I said. I'm only looking at these two terms. See, the graphs are of e power x and e power x square. I did
Oh,
not
sorry,
draw this.
I misunderstood. I'm sorry.
Okay, no problem. So this part you definitely need the x. Okay, this part you try it as an exercise. Yeah, I mean, it's okay. Sometimes I do make mistakes, but this time I was careful. I appreciate it if you point out mistakes, so don't need to feel sorry. Okay, so we do this and we go on. What do we have? Okay, so we put that back into, yeah, we substitute that. Where do we substitute? Uh, in here, x is equal to lambda q, and then x is equal to minus lambda p. For those terms, we substitute. So therefore, I write, again, I have to write a probability of Sn by n bigger than or equal to p plus epsilon is less than or equal to e power minus n lambda epsilon e power minus lambda. Was there an n? There was no n. Why was there this n? Yes, okay, there is that n. Okay, no problem. Yeah. So n epsilon times. So this p is going to be there common. This is where I sort of oversimplified. I made a mistake last time, perhaps, before correcting myself. So now in the place of e power lambda q, so I underlined that with green and with this red. So now I am going to write here in green. So lambda q plus e power, what was that? Lambda q, lambda square q square. Okay. And then plus p times, so plus q times. Now this times minus lambda q, lambda p plus e power lambda square p square, and then whole power n. Okay, that whole power n is already there, so I didn't need to use anything. So this is already there. Okay, now these two terms nicely cancel out, and so this we get equal to e power minus lambda n epsilon, and so p e power lambda square q square plus q e power lambda square p square whole power n. And now because p plus q equal to 1, so this again some convex linear combination of these two weights and then raised to the nth power, and it turns out that this is less than or equal to, so e power minus lambda n epsilon times e power lambda square n uh, lambda square n, I suppose. Yes, let me just check that whatever I have. Yeah, this is yes. I left out that epsilon. There was an epsilon present. So here also there was an epsilon. See, was there an epsilon or no? I make this. No epsilon. Oh yeah, okay, no epsilon. That's correct. No epsilon there. Okay, super. So now we can simplify this. This is equal to e power. So you see, I write here lambda. So n is common. N is common. I write lambda square minus lambda epsilon. So I add and subtract epsilon square by 4. So minus n epsilon square by 4. Okay. So again rewrite this. This is equal to, so e power n. This is lambda minus epsilon by 2 the whole square, and then minus n epsilon square by 4. Now lambda was arbitrary but positive. Okay, for any lambda. This is true for all lambda. For all lambda positive. Okay. Now what you do is you choose a one which is the least on this side, because every time this is less than or equal to. So if I replace by the least value of this, then also it's less than or equal to. And that least value, because this is a perfect square, I could make it equal 0 when lambda equals epsilon by 2. And when I do that, therefore, so this time I cannot directly write less than or equal. Therefore, I write this is true for all this thing. Therefore, this is Sn by n is less than, greater than or equal to, p plus epsilon is less than e power minus n epsilon square by 4. Okay. And now, therefore, as n goes to infinity, this goes to 0. Probability that Sn by n, see, you are not changing your epsilon. Epsilon is still the same, bigger than or equal to p plus epsilon, goes to 1, goes to 0, because epsilon is a positive quantity, epsilon square anyway is a positive quantity, minus n. So if n goes to plus infinity, minus n goes to negative infinity, and exponential something very large, that goes to 0 as n goes to infinity. That's it. So this proves, similarly, the same estimate probability of Sn minus n less than or equal to p minus epsilon also goes to 0 as n goes to infinity. And this proves a theorem. QED.
Sir, can you scroll up just a little bit?
Hmm.
Sir, here you have written E lambda square n. How did you get this?
Oh, there was a square, no, e power x square. And x was lambda q or minus lambda p and so on. Okay. So you see, this is the inequality we are using. This is why this inequality was brought in here. So it's a very tricky proof, very clever proof. I mean, I would not think along these lines to prove it. I would not be able to. How would you know you have to use this inequality? And how would you know this estimate will work? Of course, you know I mean, intuitively, you can guess that the statement must be true. Therefore, one tries to sort of fiddle with inequalities. So this is a hardcore analysis, and I cannot explain how Bernoulli thought of this. I believe that this proof itself is due to Bernoulli, but maybe I don't know about that because I don't know the history. I'm just giving you the proof that is given in the book, explaining the steps involved. So you see that's the main problem. So you need to be able to have an intuition how much of approximation you are allowed when you write this is less than or equal to less than or equal to, and then that will still yield in the limit something that goes to zero, and which convex function to use and so on, all those things. Yeah. So
Sir, here you took the E lambda square out. That is fine. But then you're left with some PQ terms. How did you get that less than equal to 1?
where
Down, down. Go down.
further down?
Yeah, here. PE lambda square Q square.
Yeah,
In this
yeah. So
line,
this again, you need to prove this. It's not some inequality. Like I said, it's kind of see, you have to have a certain function like this, e power whatever lambda square. As a lambda square anyway is a constant for us at the moment. So you look at this t square. Um, yeah, and then this t square divided by t maybe. Analyze this function where t equal to pq. Sorry, so this is not quite. Uh, no, I want to say, yeah, you look at this function and then you evaluate it at q and you evaluate it at p, and then you take this type of weighted average and compute this. And we are saying that, so this is not immediate, but I leave this out. So
Sir?
from here to here, you are using an inequality. It's so you see P and Q are numbers, both non-negative, and P plus Q equals 1. We may as well assume P is positive. Yeah. So both are positive quantities which add up to 1, and you are taking weighted averages. So that's what it means. So it's like you have P and you have two numbers. These, yeah. So mm, um, then you evaluate it at p, and then so that is this function evaluated at p, but multiply by q, evaluated at q, multiply by p. So if you do this trick, then is the property of this function or how the graph looks like should tell us that. So basically it is like if this function is like this, then it's like saying uh, you know yeah, the value at uh, so you can forget this n for the time being. So then you have to say that this is less than or this quantity is dominated by just the value at 1. Yeah. Sorry, you try and do this.
yeah, okay, sir.
I think it's an elementary fact. It's not such a deep thing anyway. The deep thing involved in this proof is knowing, okay, that this inequality, this type of thing will work. Okay, that's the difficult aspect, and that's why it's it's a non-trivial result. Okay, so
Sir?
yes.
Sir, I think for that inequality, we could do something like this because P and Q are both positive and less than 1.
Yes.
So we can raise p to the q squared to p and q to the p squared to q. So that what is, and like p to the q square plus q to the p square will be less than p plus q because p and q are positive and less than 1. So then it just goes away because it's 1 to the n.
So you are saying raise it to p square, you are saying, and raise it to q square. Is that what you are saying?
Not exactly, sir. So I'm saying we have p to the q square that is less than or equal to p because q is less than 1 and
Okay,
positive.
okay,
So,
okay. P, so, Anyway, I suppose this is an elementary thing. One can do it. Let me not dwell on that too long. Okay, so because of this estimate that we have got here, okay, this type of, here this is decreasing exponentially. Yeah. Okay. So exponentially in n. Epsilon is fixed, but you have e power minus n times some constant, positive constant. Okay, so this type of inequality, which is going down exponentially, often leads to stronger results. And that stronger result, I will explain what it is. So define yeah, so let me just check this. Yeah, Bn to be the set, which is, I think, maybe all omega in capital omega, such that Sn by n omega, Sn omega by minus p, okay, in absolute value is less than or equal to epsilon. Okay. So what we proved was probability of Bn goes to 1 as n goes to infinity. This is what we proved. Okay. You can prove more. So consider intersection of Bn n bigger than or some equal to some m. Okay. So what does this mean? This is the set of all omega in omega such that Sn omega by n minus p in absolute value is less than epsilon for all n bigger than or equal to m. Okay. For all n bigger than or equal to m. Okay. In other words, what you are saying is, yeah, so from some stage onwards, you want this inequality to be less than epsilon. Then also probability of, so this is corollary of the proof, intersection of Bn n bigger than or equal to m. Okay, this goes to 1 as m goes to infinity. So this is a much stronger statement than just saying that, you see, Bn may be large, but if you take intersection of all these Bn's, that may become smaller and smaller. In other words, what we are saying is, see, in terms of intuitive understanding, what are we saying? Go back to the statement of the theorem. Okay, the theorem is written here. If you look at the average value, that goes to 1 as n goes to infinity. Now, what this is saying is that the probability that the average value is between p minus this thing and this not just for just one particular n, from some stage onwards, okay, for every n, that goes to 0, goes to 1 as n goes to infinity, as m goes to infinity. Okay, so this is a stronger result. So because of this statement, so not only is this probability of this set, this particular set goes to 1 as n goes to infinity, you impose it, you are looking at much smaller set of omega. I hope you realize that. Okay, so now this one, why so? So we can use, this is because of proof. So you compute again the probability of the complement. Probability of the complement will be complement union Bn complement n bigger than or equal to m. But this is less than or equal to sum over probability of Bn complement. Okay. Bigger than or equal to m. And
Sir?
now, yes.
So could you repeat what you said about it being a stronger statement? I don't understand.
You see, you are taking a much smaller set now. Not only are you imposing that each, your previous statement only said probability of Bn goes to 1 as n goes to infinity. But you are taking intersection of various Bn's and starting from some stage m onwards. Okay?
Oh, okay.
So this is a much smaller set. It's a really much smaller set.
Yes, correct.
Yeah. So so again, look at the complement. This is probability of union or Bn complement n bigger than or equal to m, and that is less than or equal to, so probability of the union is less than or equal to sum of the probabilities of the individual sets. But each one of these Bn complement, there is a contribution coming from, from the positive side and the negative side. So that becomes, this is dominated by summation. What was the last thing we had? E power minus n epsilon square by 4, but it becomes twice because there are two n's to this. 2 times e power minus n epsilon square by 4. And this is from, okay, bigger than or equal to m. So here n is equal to m to infinity. Okay, why is this 2? Because there are two sides, no? When you say this is bigger than or equal to epsilon, there is those for which Sn by n takes values bigger than or equal to epsilon plus p, or takes values less than epsilon p minus epsilon, and that also has the same estimate. That's why there is a 2 here. And now this is 2 times the geometric series, and we are looking at the tail end. So this goes to 0 as m goes to infinity. Since summation, well, 2 times e power minus n square n epsilon square by 4 converges. Sorry, I had to squeeze in here. Yeah. Okay. So from some tail end, definitely that goes to 0 as m goes to infinity. That's it. Okay. Yeah. Some more remarks. So there was some exercise given. What's the exercise? I need to look at. Okay. I don't want to discuss the full exercise, but just tell you some hint. Let xn is equal to Hn minus Tn. So the notation is as in our earlier proof, where okay, Tn was not defined, but yeah, Tn is equal to number of times tail. So in n point tosses. Okay, so given that Hn as before, okay, given that probability of H is equal to P, and of course probability of tail is equal to 1 minus P, which we have been calling Q. Okay, show that probability that 2P minus 1 minus epsilon less than, so given epsilon positive, this is xn by n less than 2p minus 1 plus epsilon. This goes to 1 as n goes to infinity. So I just give you, I don't know if I should give you hint. Maybe you try it by yourself, and if you are not able to do it, you can you can have a discussion on this in the tutorial. I would like you to try this. Okay, so it's only some another 15 minutes, I suppose. I don't know. Okay. Now, I want to discuss. So I sort of briefly already hinted at discrete random variable and continuous random variable and so on. Never formally defined it. In fact, formal definition. Yeah, whatever I said, it was. This is now we discuss quite formally, and so we move on to the next section. This is on discrete. Okay, I don't know what is the next title is called. I think maybe. Okay. Discrete and continuous random variables. Okay. So this is the next section that we want to discuss. We don't want to waste time. So let me formally define what is a discrete random variable. So let x be a random variable, and let me recall for you, x is a function from omega to r, be a random variable. Okay, let fx, f is equal to fx, denote its distribution function. Okay, so recall again, that means that f is from real numbers to 0, 1 with what is the connection between x and this. So f of x is nothing but probability of the set, which we simply write x less than or equal to x. But this abbreviated version of the set omega in capital Omega such that x omega is less than or equal to x, probability of this set. And therefore it takes, of course, values between 0 and 1. Okay. So here is a formal definition of, we say that x is a discrete random variable, if x takes values only countably many values. Okay, so say x1, x2, they need not be in any increasing, decreasing order or anything like that. And it could be, for example, rational numbers. It could be anything, but only countably many values. It could be finite also. Okay. Say, yeah, this doesn't mean, okay, xn or xk, k in natural numbers, whatever that is. In this case, we define the mass function. Sorry, I can't control. Okay, sorry about that. So, function. We defined a mass function, probability mass function, or something like that. F of x. F. Yeah. Increase from this set. Let me just write it like this. Okay. 2, 0, 1 as f of xk is equal to probability of x equals xk. So this is, yeah, we'll do examples in a few minutes, but first let's go on with and finish the definitions. In this case, f of, what is f of x? This is equal to probability that x is less than or equal to x. Okay, and that's same thing as, now it's going to be a sum. Yeah, so if they are in the increasing order or something, then you can write here. But here I have to write xj less than or equal to x, such that probability of x equal to xj. Okay, and that's same thing as sum over, okay, the same set of values, xj less than or equal to x, f of xj. And so now what is a continuous random variable? So this is again a definition, random variable x. So we say that x is continuous. X is a continuous random variable random variable. If there exists a function f from real numbers to 0, 1, I suppose. I think this, let us not write 0, 1 here. Don't want to say that. See, yeah, it's just a matter of okay, let me write here 0, 1. I think it's okay to write 0, 1 such that I need to think about that a bit. Okay. F of x is equal to integral minus infinity to x. I integrate ft dt. Now, this must make sense. And we don't assume that f is continuous. So the correct terminology is, so we assume that f is integrable. Integrable. If you have studied this notion, that's fine. Otherwise, just think maybe it is, a Riemann integrable at the moment. Okay. So this word is loaded with a lot of meaning, which is why I sort of hesitated to write 0, 1 here, but doesn't matter. Just write this. Okay. It's all right. So there are, one can have random variable which is neither discrete nor continuous. But we will not study them so much. We will not study them in this course. Okay. So there are these what are called singular random variables. So you cannot write the here this function f as the, what is that? Okay. So I should say, before proceeding further, the function, the definition of the function f is called the density function. Density function of f. Okay, the probability density function of x. Okay. Let me say the following thing here. If you just let's just assume for the time being that f of x is a continuous function, little f. Okay. But I may change the value of f at a few finitely many points, and then also the value of the integral doesn't change. You all know that, right? And that's why this density function may not be unique, but as an element of something, it is unique. What is that something? That is written as L1 of R. Let us not go too much into it, but I just want to say that there can be a non-uniqueness phenomenon when you look at f, whereas in the discrete case, the mass function is yeah, this automatically, there's only one choice. I mean, this is already defined. F of xk is equal to this. Okay, in the case of mass function. Uh, Rather than proceeding further with the theory and so on, let me just tell you what you should picture when you talk about this mass function, density function, and so on. And then I will illustrate by an example today itself. Okay, so you see, x is a random variable. At the moment, just forget about the domain, but concentrate on the image that it takes. So it could be that x1, x2. Let's just look at the simplest situation where there are only finitely many points in the image, xn. And you should think that this fx is a weight here assigned at this point. So fx1 is a certain mass. So you must think of these x1, x2, blah, 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 xn as particles, and each one having a certain weight or a mass. Okay, this is fx2 and fxn. Okay, and now this is these are going to be probabilities, and therefore the mass must of course be bigger than or equal to 0. And then since you have said already that x1, x2, xn, they are in the image of a random variable, we may as well assume that these are all positive. So none of these are 0. And then, of course, the summation fxi has to be equal to 1. So fxi positive and summation fxi is 1. And essentially the same thing happens when you have, countably infinitely many of these xn's. And when we talk about, so also, yeah, there is one other possibility, neither discrete nor continuous. Yeah, the word continuous does not necessarily mean that it is discrete. This is another phenomenon. Yeah. Just a minute. I need to get one more page. Okay. Something else I wanted to say, but I got a little distracted. I wanted to say, yeah, there can be, yes. Let me, before I make this comment, let me talk about continuous, how you should imagine continuous random variable. So let me just draw this figure here for capital F. For capital F, so y is equal to capital F. That graph is what I am drawing now. So here is a x-axis and these are y-axis. And here, of course, we never cross this one. Okay. Okay. Another graph is going to look like, first of all, it's going to be a monotone function. So maybe it is remaining flat. And then somewhere it picks up something. And then maybe it goes like this. And then, and from some stage onwards, it becomes maybe asymptotic. This type of thing can happen. Sorry, so here, let me erase this because I don't have much space. I may just make this side equal to blue a little more, and it is 0. And so I'm going to draw this 0 up till here. Okay, so this is how you can imagine your capital Fx is. Now, to say that this must be a continuous random variable is to say that there is some function f, which is what I'm going to draw now. Okay, so Let me draw. Okay. Now there is some continuous function. So I may not draw exactly this. Just 1 minute, please. Sorry about that. Okay. So typically you should imagine that there is some function. Okay. Sorry, I draw it in red maybe. Y equals f of x. And don't take this very seriously. Then what happens? So this is remaining at that point like this, and then for some time. So it's some continuous function. So here is remaining flat, and then again that means that it's again coming back to 0. Okay. Okay, somewhere here I think it will pick up. Don't take this graph too seriously. I complicated things for myself. Okay. So let me make things a little more make this continuous so that the concept is okay. This is so from here onwards the graph is going like this, and then maybe like this, and this is asymptotic. So what you are doing is you are just computing. So this is x-axis. Let me complete this. Sorry, this is x-axis. Green stays flat along the x-axis up till here. And then, so from this stage onwards, you start computing. Maybe I should just make this continuous here also. I try and make things complicated. Yeah, okay. So that is typically at any given point, just look at the value of this function. That's equal to area under the graph. So here let us say x naught, and here is x naught. So area under the graph, it begins to have a graph only from here. This area is exactly the value at this point. So f of t, f of x naught is equal to area, the shaded area of the shaded portion. Of the shaded portion. Part when equals fx naught. Okay. So this is a relation between this. Things begin to get a little complicated when you have mixed ones and so on. We will see examples nevertheless, okay? How to draw these graphs of various things. I wanted to do one example today itself. Maybe I do one example. Perhaps that was already discussed previously, but let's just do this coin toss. So x is equal to indicator function of h, probability of h is equal to p. Okay, and then what is the So x, so f of x is equal to, so this is 0 if x is less than 0. And the moment x is equal to 0, it will have positive probability. So this will become P. And here, sorry, Q. And this is if 0 less than or equal to x, strictly less than 1. And then 1 if x is bigger than or equal to 1. Okay. So you can verify this. And now, what is the probability mass function? So f of 0 is equal to q, and f of 1 is equal to p. Okay, so that when you look at f0, we can now look at any value. For example, you can compute f half or whatever. Okay, so so you know how to express fx in terms of little f. So this is the thing, and now you can draw the graph of capital F and also the graph of small. Yeah. So graph of capital F looks like this. So it's flat here up to 0 up till here, and then it picks up Q and goes on up to here. Q is here, it is open, and then onwards it is just flat at 1. So this is 1, this is Q, and this is 1 here, this is 0. So this is graph of y equals fx. Okay, so here you cannot draw the graph of this one, but discrete values only it will appear take, and there you have point mass. So I just write here at 0 and at 1. This attains a mass equal to Q and attains a mass equal to P. That's it. So just 2 points. I think I'll stop here for today. Already I ran out of time. So we'll continue on Monday next week.
Thank you, sir.